Okay, for the first hour today, we're going to continue with our study of chaotic networks, and then Jonathan will come for the second hour and start a brand new topic, which eventually will come back around to being an extension of this topic, but you'll see that maybe in a week or so. First of all, is there anybody who hasn't yet taken notes and would like to take notes in exchange for 3 bonus percentage points? Excellent. You got it. Okay. Yeah, about the last class? Yeah, in a second. I want to start even before that. I just wanted to say about the conference last week. So I thought we had a great success, especially on the first day of the conference, in having at least 3 different lectures that were pretty highly related to things that we've seen here. So there was a talk, Yoram Burak, who's here at LSEC, talked about basically used a ring model with the spontaneous bump that we saw and some kind of noise, and saw how the ring would drift given if it had noise. Misha Tzadiks from Weizmann spoke about basically a Hopfield model as a model for memory recall, modeling the way people recall just a list of words, and added some hierarchical structure and things like that. And then Marcus, what's his name? I forgot his name. This Italian young man from Columbia University spoke about Hopfield-like memory models, but with bounded synapses. Exactly the issue that Jonathan introduced, where the capacity, once you bound the synapses, the capacity is reduced from something that could be proportional to n to something that's just log n. And we were talking about it with him at dinner, and just to think about what that means. If you have a brain of the size that we have, like 100 billion neurons, log n becomes something like very, very small. Like the number of kind of memory patterns you could store could become down to the order of 10 to 20 or something like that, which hopefully we can do better than that. And their model involves adding kind of hidden variables into each synapse. Isn't just a Jij that goes up or down, but there's a whole sequence of hidden variables behind it. And the effect of that is lengthening the time scales. So just a brief review of what we saw there. I also wanted to make a comment about the exercise. Okay, first of all, I guess I'll ask you guys, what did you think about in the qualitative question in the analytical problem, the first problem? So we had this Hopfield, but with a certain probability, any given synapse could be either doubled or erased completely. So we called that multiplicative noise, and then asked you, how do you think that might compare to a case of additive noise? Any thoughts on that? Yeah.
Both have similar effects. So it seems like both increase the variability of the noise. They both decrease the SNR and the capacity. But it seems like in a way the additive noise is uncontrolled because it doesn't depend on the number of memory patterns. Maybe like the extreme case where C equals 1, then the noise the intrinsic noise is 0. The variability is 0.
That's an interesting question about the rate. So the first observation I think is right. If you separate it into signal and noise, then like basically what you saw in the exercise I gave you, the signal is essentially unchanged. The signal winds up summing over these kind of random look at the multiplicative terms, but anyway that sum over large n is anyway going to give us 1 basically, and you'll see the same thing if you add some kind of additive noise. So in both the cases, kind of the signal is unchanged, and then you have a broadening of the distribution, so you're adding to the noise. And it's somewhat, first of all, even before we get into an analysis of how it might depend on the number of patterns, it's a little bit surprising that it sort of doesn't matter. A lot of times multiplicative noise is kind of very qualitatively different effect in different systems. And here, I guess due to the kind of just summing over, the system winds up summing over all this randomness anyway, so it sort of doesn't matter what the source of the noise is on that level. And I haven't thought enough myself about the dependency on the memory patterns to know whether that's true.
Yeah, it's unbound. If you increase the multiplication
he multiplies it?
It's
The
worse for
variance?
small p than the same for very large.
Uh-huh.
Why? But it's not 1 over n, it's 1.
Okay. Well, good. We'll come back to it. And the second question, did you see any interesting images in your correlation function plotting the correlation matrix? So what I worked very hard to try to find a parameter regime that might give interesting pictures was supposed to look like something like this. You have the correlation. Right, we were plotting the correlation between points at different times when we kind of had added noise to allow the system to potentially come out of fixed points. And at least what I worked very hard to set up was the kind of picture where you have these kinds of squares and potentially somewhat overlapping kinds of pictures like this, right?
Yeah.
So things like this. So it means that like during this time period, the network was around points that were all very similar here to each other, and then at some point it kind of switched out, but they were still had some similarity with these points, but then at some point you come into a new, and that at least is supposed to be reminiscent of the picture that I drew when we talked about the spin glass system and the landscape of the energy function. If we were to be able to draw the energy function landscape, so we would see these valleys inside valleys. And that's kind of represented by these overlaps of similarities. So everything's inside one valley, so there's a certain similarity globally, but then inside that, there's kind of smaller and smaller valleys, and within that, different potential local fixed points are more and more similar to each other with this kind of hierarchical structure.
And what is that then? Closer fixed points?
Yeah, more similar fixed points, and then the valley is kind of what's referred to as the basin of attraction, kind of how much noise you would need to eventually kick the system out of that valley. So at first the system starts out in its small valley, kind of things are very similar there, but eventually with the noise that we put in by flipping random neurons, we eventually escape that little valley and we go to a nearby valley, but it's kind of all valleys inside valleys.
The number of fixed points, so the Hawke speed is substantial when we talk about having p fixed points, and the larger the p is, the more dense they are. But for the random one, we didn't know if it's exactly n fixed points, or we know from the dimension of the matrix, we know.
Right. So it's a good question, but already remember in Hopfield we don't have only p fixed points. We have p fixed points that we're interested in as memory patterns. But even when we had p equals 3, we saw that there were additional fixed points, right? So all kinds of overlaps between p. So it turns out in Hopfield actually the total number of fixed points is exponential with p, because as you increase p, every kind of combination of different p's introduces a new possible mixed fixed point. And then also one thing I should point out, what you should have seen happen when you did Hopfield side by side with this and you increase p, as you increase p, you get closer and closer to this. And we maybe have brushed over it a little bit, but that's analytically also what happens. When you take p equals n for Hopfield, then you're at a case of the matrix is just totally random Gaussian, full rank matrix. So at that point, when p equals n in Hopfield, there should be no difference at all to this purely Gaussian Jij, symmetric Jij.
I think it was pretty random. It's like some of the times 120 was more close to this than 300. It wasn't very systematic.
Yeah, that definitely could be in terms of the individual instantiations, and it depends on the initial starting point. I think maybe if I would have told you to start specifically with a memory pattern, then you might have seen the difference more starkly. Right, like in Hopfield, the same matrix, if you start with a memory pattern, it's going to be pretty stable. So you'll see kind of just, that correlation matrix might just look like this, and then maybe at some point there'll be some more dramatic switch. So the fixed points kind of have more separated and distinct valleys. So like this would be one memory pattern, and then it'll be pretty stable for a long time. Eventually the noise might succeed, and then it'll kick it out to something that's significantly different. You don't have these kind of hierarchy of similarities, at least in the standard Hopfield model. Okay, so now let's go back to chaos, and there's a question about that, but I'm going to do a quick review of what we saw last week, so then you can ask if it's not answered then. Okay, so we have our model for this chaotic network. SI dot is minus SI, tangent hyperbolic. Remember, I subsumed the beta parameter just into the Jij matrix. So we write our whole dynamics like this, where we have Jij is a totally independent Gaussian matrix, each Jij independent from a Gaussian with mean 0 and variance j squared divided by n. And we can recall in terms of the parameters, the original parameters, we had a beta and a g, and our j parameter here is just equal to beta times g. Okay, we saw that based on the eigenvalues of this random matrix, which have maximum value basically j, so we saw that for j smaller than 1, we just have a fixed, 0 fixed point. I didn't prove that that's a globally stable fixed point, the only fixed point of the system, but it turns out to basically be, with high probability. Again, this is hi, so input to neuron I. With high probability, just every neuron's input is 0, its activity is 0. But when j is greater than 1, we have chaos. And what we showed last week was that we can, in the setting of chaos, so we can look at hi, the input into neuron I, and see that it's going to be a Gaussian. It's going to be Gaussian distributed across the neurons. It's actually going to be a Gaussian process in time, which we didn't really get into defining. Hi. So, and we found that still, if we looked at the average, both over time and over the neurons of the input, the average is still going to be 0. But individual neurons now differ from one another and also can potentially fluctuate in time. And I didn't prove to you that it is going to fluctuate in time, but I just kind of suggested now that it's possible, that it's possibly self-consistent that they do that by looking at the variance of hi. The variance of neurons over time, average in space. Right, I write this as a variance again because the mean is 0. So usually in the variance, I take the mean of the square minus the square of the mean, but the square of the mean is just 0, so this is equivalent to the variance. And we wrote it sum over j, jij squared, and then the variance basically in the activity. And this sum over the neurons, given our scaling of the variance, right, each term of this is just j squared over n, so we get j squared. And I basically argue that this suggests that at least it's possible for fluctuations to reverberate in the system and be self-propagating, because if we have temporal fluctuations in activity, that will drive order 1 temporal fluctuations in the input. And then we can think about the firing rate activity as a function of the input. We know how to write that in principle because we here just have a linear differential equation. We know how to solve those. SI of time in principle has this integral over past time with the exponential filtering of the input at past time. So at least in principle, we can write down SI, and then we can also in principle write down the temporal variance of SI as a function of HI, of the temporal variance of HI, some function, which we don't know what it is. So in principle, we have kind of this closed loop set of equations that can really justify this phase transition into chaos, where fluctuations are self-propagating within the system. F some function, solvable, but we're not going to do it here. So that fluctuations in the activity drive fluctuations in the input, fluctuations in the input drive fluctuations in the activity. Okay. Yeah. Yeah. Right. And you can, I mean, one way we tend to set JII equals 0. But a lot of the assumptions that we make depend on those kinds of assumptions of independence. So we assume that HI, so we can assume that HI is not dependent on SI for a given neuron. The neuron's activity. Through other, right. And so there are subtle assumptions here about the kind of loops that are created between other neurons. One of the key things that I argued is because we broke the symmetry, that's at least one, that's the primary loop that could have affected us. If we had Jij equals to JJI, then my activity would be self-propagated right away through the reciprocal connection. And then I couldn't make this assumption about the independence. So that's at least one argument to try to go towards justifying that assumption of the independence. But it's true that in general one has to be like very careful about exactly those kinds of things. So. That's J. I mean, once you're taking the average over the population, it no longer matters. But yeah, that's J. Yeah.
In the class, you talked about two different options for Jij, one without square and one with square.
Yeah.
So in the first one, you use like J wave. I just wanted to make sure it has some meaning.
No.
Like when you did it.
Yeah.
Talking about averages.
No meaning at all. Just saying, like, they could be different parameters. Could be the same parameter. Yeah. So I want to also mention that. So I argued also that this model is equivalent, effectively, to a model in which Jij is just plus or minus j over square root of n. Even though the distribution of the Jij's looks different here. It's this binary distribution, and here it's the Gaussian distribution. But eventually, through the sum over Ji Sj, Hi is anyway going to be Gaussian, even if this is our distribution. So they wind up being statistically identical. And then we looked at the quote-unquote excitatory input in this network slash the inhibitory, excitatory and inhibitory, where each plus or minus square root of n j over 2 times the average activity of the network. It noted that this is a little bit bizarre in terms of scaling, because it seems like the kind of amplitude of the input grows as a function of the network, and it could be very, very large. But this winds up giving us the variance across neurons, and also that same variance across time, which is order 1. As opposed to the other possibility of scaling, where if we had Jij equal plus or minus j over n, where in this case we would have something more reasonable kind of in terms of these mean contributions to the input. These would be then order 1. But the variance in this case of the scaling j over n, every neuron is totally identical and fixed in time. The variance is approximately 0. Specifically, it scales as 1 over n. And this kind of scaling of single synapses is 1 over the square root of n, and the scaling of the net input is going to come back to us in the model of balanced excitation and inhibition.
Why is the variance order 1 bigger?
So it's more interesting in the sense that neurons can be different from one another, and also they can have this temporal dynamic, this chaotic temporal dynamics. Because also both the fluctuations in time, the variance in time and the variance in space, can be order 1. So in that sense, it's better. Jonathan will kind of get into the modeling considerations in terms of modeling real cortical activity that then wind up kind of justifying this kind of scaling in the excitation inhibition balance model. Okay, so we did all that, and we don't yet really have kind of any clear, strong argument about about chaos really in this model, just kind of a suggestion that it's possible that fluctuations here lead to fluctuations there. So what I want to do now is also introduce more formally another part of the definition and analysis of chaotic systems, and then apply it here. So what we're going to study now is what's called the Lyapunov exponent. And this is also, in terms of the definition of chaos, this is related to the sensitivity to initial conditions. Okay, so we said the definition of chaos is that a system is chaotic if it's deterministic and has aperiodic dynamics and is sensitive to initial conditions. So now I want to define what that means. So let's go to an abstract system. We'll forget our particular network for now, and we'll just think about, we have some kind of state space X in a dynamical system where X dot vector, or I'll write it, X dot I is some function Fi of the full state of the network. Okay, so think about X1, X2, and X3. We have some point in state space X0. And if we have the network at the state X0 at time, say, T0, then we may have some trajectory X. X is a function of T with initial condition X at time T0 equal to X0. And we want to ask, how sensitive is this trajectory to perturbations in the initial condition? So I'm going to add a little perturbation, delta X, to get to point X0 prime. And then ask, what does this trajectory do? So we have a perturbed trajectory, X prime of T, with X prime of T0 is equal to X0 plus some delta X. Okay, and then we can define the difference between the two trajectories. So we'll define delta X of T as simply X prime of T, the perturbed trajectory, minus the original trajectory. And then the definition of the Lyapunov exponent, and specifically this is the definition of the maximal is the maximal Lyapunov exponent is lambda, such that the norm of the perturbed trajectory over time, for small time, for time near this initial conditions, will be approximately equal to the norm of the initial perturbation with an exponential decay e to the lambda t, or an exponential, not necessarily decay, an exponential function, which may be decaying, may be diverging. And so this lambda exactly kind of tells us the initial, just like small time propagation of this trajectory. Do the differences immediately fall off, and the trajectories essentially track one another, or do the trajectories run off in different directions? And so if we look at this, we see we have some size of the initial perturbation, If lambda is negative, then this is a decay, right? And if lambda is positive, then we have, at least initially, a deviation and an exponential deviation of the trajectories. Okay. Now, let's look at the system. So lambda is this exponent by which you can approximate. So it's kind of a definition that's assuming that we can write it in this form, and then once we write it in this form, for at least for small times, then that exponent, and we'll see it a little bit more concretely right now. So we'll see the connection.
But so when it's negative, these trajectories converge at some point, and if it's positive, then they differ.
Yep, that's the basic idea. Yeah, that's the basic idea.
And lambda isn't a function of the initial delta. Like if
so in practice, numerically, it could be, formally the definition is in the limit of small perturbations. And in that limit, at least for smooth systems, there's a well-defined lambda that doesn't depend on it. It's true that in practice, you could find a situation where very small perturbations decay, but if you make a perturbation that's a little bit bigger, all of a sudden you have something that diverges apart. Yeah, so let's see here how we go forward with analyzing it. So let's look at this perturbed trajectory. Follows the same equation of motion, right? The same dynamic equation. X dot prime of t I is fi of x prime, right? So let's look at for time t near t0. So for t0 at near t0, x prime is effectively near x0 plus delta x. So there we have x dot I of t is approximately equal to f of x plus, right, now we're doing a Taylor expansion in multiple dimensions, right? Let me write out one more step of it. So fi of x plus delta x0. And now I'm going to do a Taylor expansion. So the first 0th order term is just fi at the point x, or fi at x. Let's leave it at that. Fi at x. X can change in time, so we'll leave it like that. Now, the Taylor expansion in multiple dimensions, we're going to sum over the different components. We have the partial derivative of fi with respect to xj times delta xj. Right, and we notice this term here is the Jacobian, which we'll write it as mij is just the partial of fi with respect to xj. Okay, so this is the dynamic equation for the perturbed trajectory, and then we can look at the dynamics of delta x as a function of time. What we defined as just the difference between the trajectories. So if we just subtract, so this is just x dot prime, so x minus x dot. We can see in the Taylor expansion, right, the leading term just drops. Fix is common to both terms. We just get that the delta xi dot is just equal to sum over j mij delta xj. Or in vector form, delta x of vector dot is equal to M matrix, which is the Jacobian of the dynamics, times delta x vector. So we've linearized the system not around a fixed point. So this is very similar to things that we've done all throughout the course, where we normally had a fixed point where fi was just 0. So here we don't have a fixed point, but we're looking only at differences between trajectories. So we essentially ignore that leading term by subtracting two neighboring trajectories. And then we just have the linearization of the dynamics, just as we've seen before. And these are things that we know how to solve very well. So at least in that linearization, now come in the eigenvalues and eigenvectors, right? So the way that we'll solve this, of course, is by writing out the eigenvectors of M, and we'll find that the dynamics delta x along any given eigenvector at time t will be equal to delta x along that eigenvector at time 0, where this exponent lambda, that given eigenvalue, times time. And then essentially, as long as there's some spacing, or it might not even matter really. Essentially, then when we look at this kind of term, how does the norm of the overall perturbation decay? We're really just going to look at the maximal eigenvalue, because we basically assume all the other elements decay because of the exponent. They're going to be very quickly negligible relative to that maximal eigenvalue. So we'll just argue that delta x, the norm, is essentially delta x0 times e to the lambda max of t. And it's an equivalent definition, more common. This is the more general definition here. We can think about a whole set of Lyapunov exponents by not just looking at the norm, but by really looking at the whole set of eigenvalues. And so essentially, the Lyapunov exponent, the maximal one, is just the maximal eigenvalue of the Jacobian at any given point along the trajectory. And if that maximal eigenvalue is above 1, is positive, then the trajectories diverge. And it's really very analogous to the way we study fixed points, where again, if we're looking at a fixed point and the eigenvalue was positive, then it means the fixed point was unstable. And that really meant the same thing, right? Nearby points would diverge away from that fixed point. Here, we're just not on a fixed point. We're on a moving trajectory. But if that largest eigenvalue is positive, then it means nearby trajectories are diverging from one another. Yeah. So I mean, the size of the eigenvalues, in some sense, is the rate of divergence. Yeah, it's a question of what that means. How is that relevant to different time, to some particular time scale of the system? But yeah, you can look at both the rate, kind of in the sense of the amplitude of the eigenvalue, but also the number. It turns out to be interesting in different studies of chaos how many of the eigenvalues are positive. And in some sense, it means it relates in ways that I don't know. It relates to the dimension of the chaotic attractor that we spoke of. So if we have trajectories where there's some large number of eigenvalues that are all positive, it sort of means there's a whole volume of state space, a bunch of different directions in which the trajectories are diverging. We could have a place if we only have one eigenvalue that's positive, then essentially there's just one direction in which they diverge. Perturbations in all the other directions could collapse, and only one direction has a divergence. If we have a lot of eigenvalues that are positive, then we kind of have a higher dimensional chaos.
So the kind of system is chaotic only if lambda, some lambda is positive?
Yeah, if there's at least one. And now, a subtle thing that also I'm not familiar with in terms of the literature of chaos is this depends on the point in space, right? This whole analysis is a Jacobian M at a given point, x0, right? So this can give us very different things at different points in the state space. And so there could be situations in which certain regions of the state space have a positive Lyapunov exponent and other regions don't. Okay. So now we want to see how the Lyapunov exponent looks like in our system, right? In our network with the random Jij. Okay. So in the analogy to the abstract system that we wrote here, this whole term here, this is Fi of S, right? So essentially what we want to calculate is the Jacobian of Fi, the derivative, the partial derivatives with respect to the different components of S. So, all right, MIK, I'll just use the element, the index K, to avoid confusion with the J that will come up here. So dFi dSk. Okay, so what do we have when we just take the derivative of this? So the first term, that's -1 only if k is equal to I, and it's 0 otherwise. So we get a delta Ik. And then here, what happens to the tangent hyperbolic? So first of all, we want to take the derivative of tangent hyperbolic of this whole sum, Jij, Sj, relative to Sk, right? So there should be a minus here, right? Minus delta Ik. We'll have the derivative of tangent at the given point that we're at h. So what's the derivative of tangent? 1 minus tangent squared, which is equal to secant hyperbolic squared, which I'll write because it's shorter, secant squared. And I'll write the sum over Jij, Sj as hi, as we've done before, times, and now we have to do the derivative inside by chain rule, so we're going to pull out only Jik, right? So this whole thing is our Jacobian. In other words, following exactly the steps that we take here, we can write the dynamics of a perturbed trajectory. If we have now S prime of I, the new trajectory, is going to be Si, the original trajectory, plus the perturbation, the deviation in the trajectory. We can write the dynamics for delta Si dot using our Jacobian matrix. This is going to be minus delta Si plus the sum over K secant hyperbolic squared Hi Jik delta Sk. And now I'll define this term, secant hyperbolic Hi times Jik, as a Jik matrix. I'll call it Jij tilde. Jik tilde. And we can write in vector form, delta S vector dot is equal to minus identity matrix plus this J tilde times delta S. This one? This one here? So I have the Jacobian, the Jacobian matrix, MIK. And then when we take the time derivative of the perturbed trajectory minus the time derivative of the original trajectory, we drop off the 0th order term, and we remained only with the Jacobian, the sum over J, Mij delta Xj. So that's really just what I did here. From here to here, I just wrote delta Si dot equals sum over K Mik delta Sk, where this is Mik. And then I separate out the identity matrix from the rest, which I call J tilde. Okay, so now we would like to study basically the eigenvalues of M. Well, equivalently, the eigenvalues of J tilde, right? The eigenvalues of M are just the eigenvalues of J tilde minus 1. So let's see what we can say about J tilde. So J tilde ik is secant hyperbolic squared hi times jik. Okay. And now hi, I argued, was Gaussian, because hi is the sum over the very large number of random independent variables. And so I argue that hi is Gaussian. And it's Gaussian with variance basically taken from last week, j squared times the mean squared of s, which we don't know at this stage because we're saying we're at some arbitrary point along the trajectory. So we're at some point h, which is coming from some point s in the vector, but we know that hi is Gaussian with this variance. And so we can think about this new J tilde as also a random matrix and look at its statistics. So the average J tilde, what's the average over all pairs ik going to be? It's going to be 0. It's going to be 0 because the average of jik is 0. And what about the variance of jik? So here I'm going to be totally unjustified, and it's probably even wrong, because I'm going to have to make an assumption, treat these as independent, as hi and jik as independent, to at least get an estimate on this variance. And that's probably not too justified, but we're gonna do it anyway, just for the sake of the exercise. Put in some squiggles here, call it approximate. So we'll say that it's approximately equal to the mean square of the two terms separately. So we have some kind of mean square of the secant hyperbolic squared over the population over I. So that's going to be secant to the 4th hi times the mean squared of jik, the original matrix.
Why is this 0? Why is the average 0?
So the average is going to be 0 because here we have jik has an average 0, and then also even if we look at the hi, it's going to be distributed around it, but that sort of doesn't matter. Again, I have to think a little bit more carefully about the arguments here about independence, but we have the jijs are going to be averaged around 0, so the average jik is also going to be averaged around 0. These are things at the end of the day we're going to have to do numerically. So jik is our original matrix, which has 0.
Which has plus minus j.
Yeah, either way, plus minus j over square root of n, or this Gaussian.
So jk is the normal regular matrix, and this is the eigenvalue.
Yeah, this is the J tilde is the one that we want to know its eigenvalues of.
Maybe you can say again how this variance was or wasn't right.
So here I've assumed that hi is independent of jik, and I've just separated out the expectations. Maybe it'll be part of your exercise to see how far this deviates from the truth. But essentially, okay, this part, of course, we know. This is just our j squared over n parameter. And then we have some term. This depends on our initial condition. So I guess one way I could argue that they're independent is I don't want to. Anyway, I could say that I'm doing this for an arbitrary age I, which I choose, which is an initial condition that I choose arbitrarily, and then it's independent by construction of the actual matrix. So I just say I'm looking at this point in phase space and in the state space, and then everything's justified, and then it's fine. But okay, now, so what we have, at least if we follow that route and just say, okay, I'm going to choose a point in the state space randomly, then what we have is a matrix. Our matrix has some form where we have kind of this AI. I'll call it just the secant squared AI, which I'm choosing randomly, times JIK. And it turns out that there's also random matrix theory about these kinds of matrices. Remember, we saw the distribution of eigenvalues of the original Gaussian matrix was just uniform within the disk of radius j, our parameter. But now I'm multiplying every single row by some number. Right? So it turns out that a further result of random matrix theory tells us that the radius of the disk is basically changed exactly by the mean square of that term. So all eigenvalues will be distributed for this kind of matrix in a disk of radius equal to our original radius j times the square root of the mean squared of AI, this contribution that's multiplying every single row. So if we think of that contribution as a random contribution like this, AI multiplying every single row, then we're either just expanding or contracting that circle where the eigenvalues lie. And that's a result that I won't really justify, like the previous ones. Anyway, it turns out it does have interesting effects on the shape of the distribution inside that disk. It's no longer a uniform distribution, but the change in the radius is fairly simple, and it only depends on the mean squared of this random contribution. Okay. Now I'm deliberating how much to go on. Yeah. Yeah. Right. The variance. So the variance of the elements of this tilde matrix. Right. The variance are AI squared times j squared over n. Right. The variance is the mean squared of AI times our original parameter j. And so this is totally analogous to the original random matrix theory that we saw, where the radius was really just the standard deviation part, the square root of that parameter. Okay. All right. Let's take a break here, and then I'll decide if I'm going to go on or leave it at that. What we're going to want to do is get some estimate of how large this AI is, but at the end of the day, we're going to have to actually calculate it numerically anyway, which will be part of your exercise. So, yeah.
class.
Yeah.
Do you know recently they have a paper use new activation function?
Haven't seen it.
So it's basically like alpha. I don't remember the formula. So it's a new activation function, and so using deep learning. So they tell in this paper they say that if we use this activation function, so they can keep the output in from 0 to 1, and this is a fixed point. And so my question, and in this paper, so they they mainly do the calculation and things. And the calculation is very long, and 70 page. Yeah, it's very long, and I think it's very interesting. So, but at least now I think my ability I'm not capable to read it now. So, but I'm interested in this field. So, I mean, so if I want to do something related to this, do you have any idea? So, like, what kinds of things I need to learn?
Yeah. Generally, I don't know. I mean, hopefully some of the other courses here will help. I mean, the second course, theoretical computational neuroscience, kind of maybe will be a step, and also there's a course here in statistical and information learning. Good Meida Velemida. What's it called? Information learning and processing. Another course here, another required course.
Right?
Yeah. The two courses next semester. Hopefully that helps to some extent in that kind of a thing. But then it's really things that are more studied in computer science. So there's also a number of courses here in the computer science department. Although they might usually be taught in Hebrew, but maybe they could teach them in English. There's a few courses in machine learning here and then computer science in the school of computer science. Like the dependency on deep learning on particular transfer functions. I don't know where.
Okay. So do you do some related job with this one? I mean, so like
Do what? I don't know anything about it.
Okay, you don't do anything.
No.
Okay.
אתה יכול להגיע בשלב הזה ואני אשאר לפוזיטיב אבל לא מספיק הבנתי את ההבדל העקרוני שדיברת עליו בין שני סוגי הווריאנס, שיש וריאנס 2 ווריאנס 3, אבל לא מספיק הבנתי מתי בוחרים להשתמש במה, כאילו כי שניהם,
כן, זה
כאילו איך אפשר
לא היה פה עיתון, אפשר לבקש, כאילו אפשר לשאול על זה וגם על זה, זה לא עניין של כאילו יש מקרים שבו זה רק שתי שאלות בנפרד, הייתי יכול לשאול
אולי אני לא מבינה איך זה שהוא in time הוא לא in space ולהפך, כאילו איך באמת זה מתייחס רק לאחד.
אם אני מסתכל על ה-variance in time,
כן.
הדבר הזה,
כן.
אז זה שייך לכל נוירון יחיד. עכשיו, על זה אני יכול להסתכל על בעיקרון רמת הנוירון היחיד. גם יכול למצע את זה עבור האוכלוסייה. זה גם לעומת אני יכול להסתכל, למשל אני יכול להסתכל או בזמן נתון פשוט על ההתפלגות עבור הנוירונים, או אני יכול קודם למצע בזמן. להסתכל על לכל נוירון אז יש אינפוט ממוצע על הזמן ואז להסתכל על השונות המרחבית.
אבל עשית דיברת על פלקשואיישן, דיברת עליהם כאן.
לא, השאלה אם כדאי להמשיך או לא.
כמה עוד יש לך?
אז אני
גם שנתחיל חומר חדש.
זהו, אני כאילו לקראת סוף.
אבל מה?
זה
לא יכול להתחיל מתי אתה רוצה שיחכה בחוץ? כאילו כמה זמן ייקח? רבע שעה?
כן, 10 דקות.
טוב, אני אחכה בחוץ.
אוקיי.
כחלב.
About the thing you teaching today, so is that only related
There's
to
nothing from last year. No. It's new.
this new?
Yeah, this part is new.
So,
Yeah.
so we're not going to talk about this part?
I don't think we'll get to some other things, but not we'll get to we'll get to all this.
But not this one.
We're gonna skip. We'll get to here. We'll get to from here onwards. You'll see.
But okay.
We're gonna move. Jonathan's gonna start in and gonna talk about some of these things, but actually he's gonna start from here and then go back to there. So.
Okay, this part is new.
Yeah, and this part is new.
העובדה שאני יותר חוזר ונכנס למילואים, שזה משהו משנה את הילד במילואות הספציפית. זה שמישהו מסוגל לבוא ולהגיד, אתה עושה את זה ככה, פעם עשו את זה ככה, אפילו לא יוצאים את זה. לא, אנשים לא... יום אחד עוד יהיה פה צבא מקצועי. מה זה? יום אחד עוד יהיה פה צבא מקצועי. כאילו שאלה ממש... שאלה בעייתית. שאלה שאלתית. תראה, בארגון מקצועי זה לא קורה מה שאתה. ברור. כאילו אנשים פשוט נשארים לעבוד. לא, יש פה מערכת עם זיכרון ארגוני של שנתיים. זאת אומרת כל שנתיים אתה רוצה זיכרון של מערכת דאטה. כאילו... לא, אני מסכים. כאילו גם את זה משהו. לא, נכון. יש לי חבר שטען ש...
Okay, let's keep going. Okay, so we're studying the Lyapunov exponents of our random network. We derived the dynamics of perturbed trajectories, in particular the perturbed part. We found the Jacobian by finding the Jacobian, which was minus identity matrix plus this J tilde matrix, and so we're in the process of trying to calculate the eigenvalues of J tilde. In particular, the largest real part, the maximal real part of the eigenvalues of J tilde. I've argued that at least if I take a random point S in the state space, so I get HI, anyway I get HI which is Gaussian. If I take a random point S, then I can think of these two contributions to JIK as independent. And then the expected value of JIK is 0, and the mean squared will be the mean squared of this AI term, which multiplies rows, times the original variance of our matrix J squared over N. And under these circumstances, random matrix theory tells us that the radius of the eigenvalues will be J times the square root of the mean squared of AI.
And radius in what space?
And so we'll have a complex plane, real lambda, imaginary lambda, and we'll have a disk of eigenvalues where the radius is J square root AI squared, and all the eigenvalues will be in this disk in the complex plane, and we're particularly interested in the maximal real part.
Lambda I, and lambda I, real lambda I, and imaginary lambda I.
Yeah,
Each I.
yeah, and they'll all be in here in this disk. Okay, so AI is this hyperbolic secant squared of HI, and HI has a Gaussian distribution. In particular, then, we're interested in calculating the mean squared AI. So first, let's look. So it's the mean squared of AI is the mean of secant hyperbolic to the fourth over HI is Gaussian. So just to get a picture of what we're looking at, so remember secant squared is 1 minus tangent hyperbolic squared. Tangent hyperbolic squared is kind of in the edges, it's 1, and then in the middle it comes down to 0. We're taking 1 minus that and then squaring it, so we get things that look like this, and I've plotted a few different versions of it just for if we had secant to the fourth just of h, so we'll have some kind of rise to 1 and then down. If we introduce here a positive coefficient larger than 1, it sharpens the curve until in the limit we'll get something very, very sharp here that rises to 1 and falls. And if we have a coefficient smaller than 1, then it kind of spreads that curve out. That's just to give us a sense. Okay, now what does this average look like? So HI is Gaussian, so we can write out explicitly what this average is. So I can just write out a Gaussian integral average over some dummy variable dz, which is going to have a Gaussian PDF, standard, and with the variance given in this case by what we wrote as the Gaussian, as the variance here, minus z squared over 2j squared average of s squared. So that's the Gaussian PDF times just secant to the 4th z. Alternatively, we can change variables to a standard normal Gaussian. I'll let you do this at home and just write it out immediately. So now dy we'll have just a standard normal Gaussian, and instead of z inside the secant, we now basically move the standard deviation, j times square root of s squared y. So this is the mean squared of A, and we'd like to get some kind of estimate of is this going to be, if this is small, then it's going to shrink our circle, and we'll have stable trajectories. We might not have any positively Lyapunov exponents. But if this whole thing is large enough, then because our j parameter is larger than 1 already, if this is all large enough, then we will have chaos according to the formal definition. So how can we get some kind of bound on this integral? We see that what happens if j is very, very large, or if the variance of s, if those were very, very large, we would get sharper and sharper curves here for the secant, and the average then over the standard normal Gaussian would shrink more and more. So if j was very, very large, this whole integral would shrink because the curve is getting narrower and narrower. One thing we can do is we can bound this term, sigma squared term, or the s squared term, excuse me. So s itself is bounded between -1 and 1, so s squared maximally is just 1, right? So this s squared term can't be larger than 1, right? So therefore, we're going to bound this. We said, as this term, the j times this gets larger and larger, this integral shrinks. So it can't be. So the whole integral will be larger than dy Gaussian standard normal over secant to the 4th jy, and that's kind of going to give us our bound on the mean squared of A, and from there we're really going to have to turn to numerical estimates to do it. So let me just show you results. Right. Okay, so essentially we're interested in the real part of lambda max, which is approximately equal to j times the square root of the mean squared of AI. So it's going to be j times the square of AI. And showed here this is going to be larger than or equal to j times the square root of our integral. No, this is just 2. This is just the standard normal Gaussian. Squared jy. So this depends on J, and at this stage, kind of plug this into the computer and see what this looks like as a function of J. And so that's what I did, just to show you what this looks like as a function of J. So at 0, it's 0. We're really interested in the point where J is 1 and larger. We get this kind of a increasing shape. And at 1, this is equal to something like 0.68. And then somewhere around J equals 2, it becomes larger than 1. So this is a little bit less than satisfying. We found we have a bound that says if J is larger than something like 2, then for sure our trajectories will diverge, and we have like a really truly chaotic system. The bound isn't good enough to really tell us that as soon as J is larger than 1, we really get chaos. But you guys will see numerically that in fact, at least for large enough n, when J crosses over 1, the real value of before this bound, the real value of AI squared will be larger than 1, and therefore the maximal Lyapunov exponent will be positive, and we'll really have diverging trajectories. So you'll see that's actually more interesting is to see it numerically. So I'll have you guys both actually like track nearby trajectories and see the way in which they diverge or converge, and then also calculate these eigenvalues numerically for specific points in the state space.
The y-axis is lambda? Is it lambda?
Yeah, the y-axis is, well, the y-axis is this bound, is what we get from this bound.
So looks like lambda will be positive everywhere.
We have 1 minus this, right? So I've mixed up the lambdas here. Here, this is the lambda of just the J tilde component. Remember, our overall dynamics, the Jacobian is has minus identity matrix plus J tilde. So the overall eigenvalue that we're interested in terms of the Lyapunov exponent is real lambda max minus 1. So
I need to
shift everything. Yeah. We put that at, yeah. Yeah, we could put this at 0 in terms of the actual Lyapunov exponent. Okay, so sorry for the less than satisfying punchline here, but you'll see it numerically in the simulations, how trajectories actually diverge, and compare that also to the numerical calculation of the actual eigenvalues for different points in the phase space. And that's it for chaos. And I'll call Jonathan in. Jonathan.
Okay, so today we are going to start a new topic, and we are going to talk about the actual firing of neurons. We talk about membrane potential, we talk about spiking of neurons. So far we only spoke about firing rates, but now we're going to move on and talk about the timing of spikes. And as an introduction, I'll show you several examples. So this is an example, this is a classic example from Georgopoulos. So he was studying the motor cortex of monkeys. So this is an experiment. You have a monkey, and the monkey is trained to move its hand to one of 8 directions. And what you see here, this is these are the rasters, the timing of spikes in different experiments. So divided by the direction of motion, and one can look at something like the firing rate as a function of direction. I think you saw this graph sometime in the first class or second class, something like that. And so far we were interested in the firing rate as a function of direction. Now there is something that should bother you here, and I may or may have not discussed it, and this is the fact that so some of you here, I think, consider themselves as scientists, or want to consider themselves as scientists, right?
What's the problem with that? Why?
With these experiments, with the results of these experiments. There is a problem, yes. Just thinking about it as scientists. It's not repeatable, exactly. So you do the same experiment again. You don't get exactly the same results. Now, the standard interpretation in biology would be that this is noise, right? There's always noise in biology. Biology is special. There's always noise in biology. You don't say there's always noise in chemistry, right, or physics. In biology, there is always noise. Now, what are the interpretations of this noise? Well, so there's measurement noise, but measurement noise is something that improves with improving measurements. But this is a kind of nasty noise that you always see. This is from the experiment of Georgopoulos. This is another experiment in which the monkey is trained to make the same motor movement, and these are the different motor movements that the monkey made, and these are the different repetitions. And well, you see that there is a change that is related to movement onset, but it's kind of on average, there's a change. There's a problem with the timing of individual spikes. Now, you may want to argue that this is a result of the different trajectories. The trajectories are not exactly the same, so maybe there's a correlation between the variability here and the variability here, but it turns out that this correlation is rather weak. This would be another example. This is another classic study by Miyashita from 100 years ago, or more precisely from the late 1980s. And this is from the temporal cortex. An animal is instructed to memorize a pattern and then compare it to another one, same, different, and decide whether it's the same or a different picture. And these are different repetitions. You can see that it's an old study because the quality is rather poor. It's generally believed that this is a signature of the memory. But when you repeat the experiment, you get different results. Every time the pattern is slightly different. This is yet another example from a different cortical region. This is a region called LIP. Animal is instructed to make a saccade to the receptive field of the neuron. The details are not important. These are averages under different conditions, and these are just repetitions, and all these should be exactly the same, and all these should be exactly the same, but they are not exactly the same, and so on and so forth.
But this is not so surprising in such large networks, no? Because it's like statistical physics. You know stuff about the averages and stuff about the variance, but you don't know about the specific.
So it's an interesting question whether this is something that should be expected. Many things in statistical physics are actually very reproducible. For example, the pressure in this room is a result of statistical physics, and it doesn't change much.
It's something like the average. It's something you say about the whole the network as a whole.
Okay, so the question is whether this is something to be that is surprising or not will depend on the details, perhaps, of the network. And I'll try to convince you later that, in fact, this is interesting. So naively, you could say, well, I don't know, this is a property of neurons, but this is not always the case. So this is an example of an interneuron in the cerebellar cortex. It's pretty regular. So it's not essential that large systems will behave this way. This is, by the way, in vivo. This is in the living animal. So if you argue that this is a natural outcome of large systems, well, this would be an example showing you that you are wrong. And, okay, but this is cerebellum, this is a cerebellum, this is a cortex. Maybe there's something special about neurons in the cortex. This is just another, this is an example of cortical neurons. These are interneurons, fast-spiking interneurons. You inject current to these neurons, and they're pretty regular. So it's not a property of these cortical neurons, and it's not a property of the fact that the brain is large. So there is something perhaps interesting here. So this is a topic of our discussion in the next several classes. Questions? Yes.
So far we've had these distances, but we're okay with them. We just looked at the firing rate, but the way we also simulated these things, we didn't consider the time. So I'm bothered by the fact that we didn't care so far, and we simulated with things that didn't take into account regularity or irregularity, and it worked.
Well, I don't know what do you mean by we did not care. I cared, but secretly.
We usually had a time concept of 1, and we didn't consider...
There was dynamics. There was dynamics of rate. Basically, what we said so far was, this is what we care about. This is the firing rate. This is what we cared about. We asked questions, for example, how does this selectivity emerge? Dynamically, from interaction of neurons. And we said, okay, we don't care about these small things. Everything averages out. So in that sense, we did not care, but still, well, we just ignored it and behaved as if everything is okay. So now we're stepping back and looking back and say, hey, how are we going to explain these things? Now, again, you could argue that when we haven't started modeling it, and eventually there'll be equations and models, and we will not take everything into account when we will model the neurons trying to explain this. But there are many problems in the world. So we're now moving from this to explaining this to explaining.
Do we want to model Do you want to model the irregularity, or do we?
We want to model the fact that the timing of individual spikes is two things. There are two things that we want to model here. One, the fact, I think this should be really something that we should care about, is the fact that we do the same experiment again and again and again, and we get different results. This is one thing to care about. And second, the finding that the timing seems rather irregular. We will be more precise about it later. We'll quantify it in a more precise way. I mean, let's suppose that there are two things. So look at this thing here. So I don't know. Let's find a nice example. So I don't know, like 9 spikes here, and then a pause, and then 3 spikes, and then a pause. Let's say that all trials would have looked exactly the same. 9 spikes, a pause, and then we would have said, okay, we need to explain it, but at least we know that we can repeat the same experiment and get the same result. But here we have 2 issues. One, the fact that we cannot repeat the experiments. You say this is in the 80s, but this is also true today, in the sense of getting exactly the same firing pattern. And second, try to see whether we can explain this. Now, this is easier to explain, right? This is a limit cycle. Limit cycle is something that some of you at least learned in the previous course and explained how a limit cycle emerges. This is something that perhaps is relatively easy to explain. But this pattern is less easy. And we will be interested in these 2 things. Yes?
What do you mean there is a data in the difference between them?
There is what? I'm sorry?
Data in the difference between them.
You mean information?
Yeah, like something computationally or cognitively, or are we just trying to explain phenomena with something?
So let me rephrase your question. So let's look at this. So there can be, one could ask the following question. No, let's do the motor one. So one thing that you could ask is whether there is information in the exact timing of these spikes about the exact trajectory. This is one question that you could ask. And the answer is, to first approximation, no. But you could ask whether there is information here about other things. Let's say that this monkey is thinking about its favorite political candidate. So this is it is considering Bennett here, and this is considering Bibi and Herzog. So it could be, but we don't know. So, or maybe it's more hungry here than it's here, and so on and so forth. There could be information about other things that the monkey is thinking about. But at some point you ask, this becomes a philosophical question. I mean, if the brain is a deterministic system, then in some sense there's information in everything about everything. So it's kind of complicated. But let's consider it as an experimental finding that we want to consider. You have a question?
Yeah, but can you see this is actually a noise or not? Like
What do you mean by noise?
See, you have like a normal distribution or something around the mean.
So you want to? The question that you ask is about the distribution of these events. Okay, we will talk about it in a sec. More questions?
You're saying that neurons are not necessarily chaotic, or
That's a question, whether they are chaotic or not.
if it has limit cycle, then it cannot be chaotic at the same time.
So the question is, what can we say about the individual neurons? Okay, I see your question. So based on your question, let me change the order of what I was going to talk about and present some and start with another presentation. So give me a second. Okay, I will just show a couple of slides. I will try to show a couple of slides. So there is an issue of why is a firing in the cortex, is it an issue at all? So what are the possibilities? You spoke about chaotic dynamics. It's not clear exactly what you meant, but maybe we'll go back to this point in a second. So maybe this is not something to be surprised about. So what you see here, and I know that I'm ahead of time. One can ask, what are the determinants of the spiking activity in the first place? Okay, I cannot do this introduction without another introduction. Just a second. No, it's okay. I mean, there's nothing sacred about the specific order that I wanted to present things, so let me So the first thing that one perhaps should consider, the first question that one perhaps should consider is why neurons are electrically active in the first place. Now I know that some of you, the LSEC students, know everything that there is to know about it, but still it's not all of you are LSEC students. So this is an example of a recording from a Purkinje cell in vivo, in the living animal. Again, answering your question. That's a completely different pattern. It's a different. This is not the regular spiking that we saw previously. You have like these bursts of activity. This is something different. So just saying, it's a complex system. That's why we expect to see it. This is not a very satisfactory answer given the brain. So we see these stereotypic events, and this we should ask ourselves, why are neurons electrically active in the first place? So as you all know, so this is a neuron, model of a neuron, and neurons have a membrane, a lipid membrane. So this is how it's a bilayer membrane, and the reason, well, I didn't create the brain, so I don't know the reason for this, but one thing that this one outcome, or one thing that this membrane enables is a difference in the concentration of neurons in the inner side and the outer side. I'm sorry? What did I say? Ions, yeah. For me, everything is neurons. So in neurons, and this is also true for most neurons, and this is also true for most other cells in the body, there is a high concentration of potassium inside, and low concentration of sodium inside, and a high concentration of sodium outside, and a low concentration of potassium outside. Now, the fact that and what generates these differences are specific ionic pumps that use energy to pump in potassium and pump out sodium. On this lipid membrane, there are specific conductances. So these conductances are like, you can think about it as holes that allow only specific types of ions to go in and out of the membrane. And one important conductance is potassium conductance, and the outcome is because we have more potassium inside than outside, then there will be a larger flow of potassium from the inside to the outside than from the outside to the inside, which will result in a change in potential between the inner side and the outer side, and this change of potential will be the opposing force of the flow of ions, of potassium ions from the inside to the outside. So the idea is that the difference in concentrations between the inside and the outside, combined with specific conductances, results in a potential on the membrane of the neuron. Now, so the energy. So thinking about an ion that can be either inside or outside, the energy associated with the two states is given by the valence of the ion, which can be, in this case, it would be +1. The charge of the ion, this valence times the electron charge, and the potential. So this would be the energy associated with each of the two states of the ion, and at a steady state, the concentration, the ratio of the concentration inside and outside will be given by the Boltzmann distribution, by the ratio of the potentials. And from this we can draw something that is known as a Nernst potential, which relates the potential on the membrane to the difference in the concentrations. So put differently, the entropy associated with a difference in concentrations combined with the specific conductances results in a membrane potential, in a potential on the membrane of a neuron, and the Nernst potential for different ions is different depending on the different concentrations. For example, for sodium, the Nernst potential is approximately 60 millivolts, and the potassium potential is approximately minus 70 millivolts. Now, the cell can go from one potential to the other, and this is the action potential that we discussed previously. The cell can go from one potential to the other by changing the specific concentrations. So if we have, if most of the, by changing the conductances. So if most of the if the conductance of the membrane is dominated by potassium, the cell will be hyperpolarized. It will be the membrane potential will be according to the Nernst potential of the potassium ions. On the other hand, if conductances are dominated by sodium, by specific conductances to sodium, then the cell will be depolarized. So the cell can change its potential by changing the relative conductances of different ions. So this is a short introduction to why neurons are electrically active in the first place. Questions about this? So we haven't discussed the mechanism for an action potential, but the idea is that we have a form of a positive feedback mechanism. The idea is that once a cell is depolarized, sodium conductances, channels that are specific to sodium open, they are voltage dependent, resulting in further depolarization. This is a positive feedback mechanism that results in a depolarization of the cell close to the Nernst potential of the sodium ions, and then these channels close and the cell reverts to the Nernst potential of the to potential that is close to the Nernst potential of the potassium ions. So that's basically the idea of an action potential. Questions so far? So now we are talking about the irregularity. Why the spiking is irregular. Now, these ionic channels, now we're back to this figure. These ionic channels are molecules. So the difference between an open channel and a closed channel is the 3D conformation of this protein, of this molecule. Now, the changes in the state of this molecule or the configuration of the molecule, these are intrinsically stochastic. They are intrinsically stochastic. So one would naively say that the irregularity in the firing of the neuron is a result of irregularity or these stochastic transitions in the states of the ionic channels. So that's a possibility. Yes?
Something general. The neurons fire when the action potential gets to a certain level, or when the change gets to a certain level? Is it a function of the voltage, of the potential, or the change of potential?
In reality or in a model? In the model that we will discuss, it depends only on the potential. In reality, it's more complicated, and it's also a function of the change in the potential. More questions? So naively, one would say that the stochasticity, the intrinsic stochasticity, which is a result of the physical properties of these channels, may underlie the irregularity of the firing rates. Yes? Everything is because of you. You asked the question. It's your fault. You should be. Apologize to the world, the class, and Bennett.
If the probability of channel opening is very high, do you still consider this process?
Yes. Well, it's not a question of considering it. It is. You can patch a membrane and get to one channel and look at it, and this is what it will look like. This is what it will look like.
But under certain circumstances, you will see that they are all quiet.
I don't know about all. But the and again, this is not the area of my expertise. If there is an area of expertise in my case, but channels do change all the time. So even channels that are considered as open, constantly open and close. And these are the intervals. So this is a matter of milliseconds. More questions? So in principle, one could say, and actually some people say that this stochasticity contributes to the irregularity of the firing. But, well, the fact is that neurons can be very regular, including cortical neurons, including the same type of neuron that we see that fire in a very irregular way in the cortex. So it doesn't seem to be so the stochasticity in the firing of neurons does not seem to be the result of intrinsic stochasticity in the components of the cell that generate the action potential. So we need I'm sorry? Sorry.
No, I didn't say it.
I can open another presentation on a different topic. Well, I could have, but I have to run because I teach in the other side of the campus in 15 minutes. So we will conclude here. Neurons are irregular, and it's probably not the result of intrinsic stochasticity in the intrinsic components of a cell, like the ionic channels. So the implications are, if it's not intrinsic, then it has to be extrinsic. It has to reflect stochasticity or irregularity, at least. I don't know what stochasticity means. Irregularity in the input to these neurons. Okay, so why is the input to neurons irregular? This is something that we will discuss on Thursday.